Thank you for coming, staying to the very last session of the day. It's been a great day today in the science and data track, so thank you to all our speakers and all of you for coming to the sessions and making it so good. So last up, we have Alistair and Tris. And okay, bios. Alistair is a data scientist currently working in cybersecurity domain, namely identify and access management. Identity and access management. Yeah, it's been a long day. He enjoys exercise, cooking, and data science, not to mention AFL and most sports. In his spare time, he may also put together a comedy video or two. And Tris is a part-time deep learning research student, currently working in the information security domain, enjoys random strolls and food hunting in foreign cities. But today, they'll be both talking about machine learning and cybersecurity, detecting malicious URLs in the haystack. Oh, welcome them, please.
Beautiful. Can everyone hear me okay? Can everyone hear me okay? All good? Yeah, welcome. And I guess thank you for staying back. I know the boat show was probably on your mind. We really do appreciate it. I haven't really personally felt like this since I put Budgie Smugglers on for the first time, but I'll give it a go. So, we obviously just had a little bit of an introduction. This is Tris, and I'm Alistair. We've been working in information security and data science for about 18 months, and we're here to sort of share a bit about our journey as a team and some of the things that we've been doing. But first, I'll start with a little story. So, about 5 years ago, I was developing a bunch of websites for small businesses. We're talking fitness studios, just your small sort of battlers just trying to make a start. And I was maintaining and hosting them on the cloud. And one afternoon, a very angry art gallery gave me a call. And they were like, what is going on here? There was pictures of nude men all through their gallery pages. The website had been hacked. And although some, I guess, art galleries may see nude men as art, not this art gallery saw this as artwork. But in all seriousness, this is my, I guess, introduction to, I guess, just how unfair the internet can be. And it was probably my bad with regards to just not patching a WordPress website, which is pretty simple. But it was an introduction to just how, I guess, just how unfair it can be and the impact it can have. And I was certainly in shock and I didn't know what to do at the time. And it obviously cost a bit of time and effort to fix. So why are we here? There's sort of three flavours to our presentation. From a bit of probably a foreign sort of standpoint, we looked at how to apply design thinking in a cybersecurity context, namely threat detection. Secondly, we employed a few data science frameworks to really help us with our, I guess, common language in our project and how to structure it. And lastly, using Python to make our machine learning dreams become reality, just like the Face app that's out at the moment. So how our project started, typically we're actually in consulting, so typically the boss comes along and they give you a spreadsheet of really ugly, I guess, use cases. And it doesn't really motivate you. There's no sort of, I guess, journey there to get to that point. It's just like, do this. It's a line, a statement, I guess, just defining a threat detection use case. And it sort of had us at a crossroads. So we did a bit of research and we looked around online and we sort of came across this design thinking, I guess, approach. And it's all about human-centered design of products. It's putting yourself in the shoes of the end user at the start of your project and really seeing what makes them tick. Then you go along to define a problem statement. And then from the problem statement, you start to come up with some ideas, and then on to prototyping and testing. We love this so much that we sort of enforced a forced marriage with some data science processes and elements in those that we really loved. And it was all underpinned by Python. And we sort of used this framework that we came up with called the threat science framework to come up with all our sort of threat detection use cases. And it's really in its infant phase, I guess. So first step of the threat science framework is to know the user. So put yourself in the shoes of the end user, and in our case, it was the security analyst in a security operations center that we're working with, and really trying to understand their pain points, their goals, and sort of understanding, I guess, what do they do in a daily sort of context. Once you sort of do that, you nail down the problem statement. So typically, you do this in design thinking, and what it enables you to do is actually focus on a concrete problem to solve. Next up, you go into Ideate, which is where you come up with all your ideas that relate to that problem statement. And then this is when our data science process that's sort of tailored to our sort of context kicks in. And it's all underpinned by Python. So we start to understand the threat that relates to our detection use case. We acquire some data and we understand it. You'll see some common elements from the Microsoft data science process here. You do some feature engineering, do some modeling and evaluation. So you pick your candidate models, train them, evaluate performance, and then you deploy it. And this sort of goes around in a continuous sort of fashion with lots of feedback loops and here and there. Cool. So we'll take you through our journey with obviously detecting malicious URLs using machine learning in Python. So first up, we had to know the user. So this is typically done by doing things like interviewing, service safaris, guided tours, and empathy maps. And it's really about putting yourself in the shoes of the end user. So sitting in a security operations center for a day, understanding the tools that they use on a daily basis. And through this process, we're able to unveil a few key themes or challenges that we see in the security industry. And obviously, folks in this room probably know a bunch more. But the key ones that we sort of focused on were management of numerous security tools. So there's numerous tools at the disposal of security teams. And obviously, maintaining them, keeping them sort of current is a real challenge. There's this thing called alert fatigue. So folks are getting a bunch of alerts and they're sort of inundated by alerts each and every day. And that sort of diminishes performance and may sort of impact defense capability as well. You've also got high staff turnover. So obviously the environment and the context of security, there's a lot of highly skilled staff that are obviously getting poached from here and there. And that obviously leaves a skills gap in your team as well. So something in design thinking that's really handy, it's sort of a snapshot of your end user, and we call it a persona. So in our case, it was this security analyst persona that we wanted to obviously build a product for. And it's all about defining their goals, their needs, and their pain points. So here you can obviously see a snapshot, so maintaining a security architecture. You've got defend against myriad threat vectors, so they obviously want coverage across the whole attack lifecycle. The needs around rapid incident response, a rich tool set, and I obviously want some free time to work on interesting projects. No one likes to be doing the same thing each and every day, just responding to the same sorts of incidents. And obviously the pain points around alert fatigue is something that really focused on. So cool, we really had this snapshot of our end user. We're starting to understand and empathise with them. Now it's time to kick off nailing down the problem. So nailing down the problem is all about defining your problem statement. And here it's all about setting a context of the problem you're trying to solve and then defining a problem statement in terms of design thinking. So that sort of looks like the structure that's mostly used is you've got your user, their needs, and then what they benefit from that need. So here we've got security analysts need rapid and intelligent cyber defense capability so they can stand a chance against a growing and often superior threat. So cool, we had a real, I guess this brought us along a journey. We had a problem statement, we'd empathise with the end user. We're getting really sort of invested in the project rather than just looking at a spreadsheet and going from there. Now this is where the fun begins, the ideate phase. So using a common design thinking, I guess, methodology here is to use how might we statements on sticky notes. And it's just about getting a good diverse bunch of stakeholders into a room, no skeptics in the room, and it's just about putting all the ideas you can on a board. And it's really about cultivating creativity. And it's creativity from not just the creative folks, it's from all walks of life. It's all about having a diverse set of stakeholders in the room, and there's no ideas that are dumb ideas. And some common techniques used here are like brainstorming, brain writing, and mind mapping as well. And these are all really common techniques that you can sort of research online. So cool, we started to ideate, and then we came up with this big how might we statement. How might we build an automated and intelligent ecosystem of machine learning models that work in unison to provide superior defense against an ever-evolving threat landscape? I know it's a real mouthful, but it really got us excited. And that was sort of our starting point in terms of a high level how might we sort of vision. But we had to start one idea at a time, and that's one prototype at a time. So how might we detect malicious URLs using machine learning and Python? Cool, so we had a use case now. Now it's time to kick off the fun stuff with coding and get into our sort of data science process elements. So it's all about starting to understand the threat. So first and foremost, we're sort of dealing with detecting malicious URLs. And I guess there's a few different guises here. You've got the common cyber squatting where really popular, I guess, brand domains are squatted online. You've got phishing attempts, which are also related to spam, and you can just go into your Gmail sort of spam folder and find a lot of examples of this. You've got typo squatting, which is subtle differences in the domain string as well. And then you've got your more randomized strings related to URLs that are commonly used with botnets and command and control sort of vectors. So now we sort of understand, I guess, the threat that we were dealing with and what we wanted to detect. Now it was time to acquire some data. So we couldn't actually get our hands on some real world data within our organisation, so we had to go out into the open source world. And sort of consulting a few different papers, we're able to find that benign would be, our benign data set as Alexa Top 1 Million would be a good starting point. I know not all Alexa Top 1 Million websites will be exactly benign and not malicious. There's obviously some contamination there possibly, especially at the pointy end at the end, in the tail end, sorry. On the other side, you've got the malicious data set that we chose, which was Fish Tank, which is a database of phishing URLs. And then we used some enrichment. So we looked at the IANA designations, which we can get by using the first octet of the underlying host IP under our URLs to find out where the IP address was designated from. Cool. So we started to sort of build this, I guess, feature set. Some of the common, I guess, features that we saw in our data that we were able to extract using a bit of Python and a few APIs was domain creation date, consulting the Whois database. I know GDPR is probably going to have a bit of an impact on the amount of Whois data that you can get in the future. We also looked at the expiry date, so how soon is the domain going to be expiring related to that URL. The underlying host IP, if we use socket. The domain name itself and sort of looking at lexical features. We looked at the registrar or the Whois server that related to the domain in the URL, and a bunch of other ones. So doing a little bit of exploratory data analysis, I've just got some samples from our data. There's obviously some really dodgy Whois servers that we sort of were able to unveil in the form of public domain registry. So there's a little bit of, these features had a little bit of information in here that would probably be worthy for, say, a machine learning model downstream. And we sort of used Seaborn and Matplotlib to sort of plot these exploratory data charts out for us. So second, we've got creation bins. So we did a bit of binning on the creation date of the domain. And as you can see here, as you sort of get in the middle bit where you've got sort of more recently created domains, you start to see more of a malicious count. And then as you get the older domains, you see more of a sort of benign count. So obviously older, more, I guess, established domains generally are benign, but obviously sometimes they can be malicious as well. So now we've got this sort of feature set. Now it's time to prepare it for our machine learning phase. And things that we used in here were things like normalization, standardization of our continuous variables, embeddings for categorical variables by leveraging the FastAI API built in Python, and its underlying architecture is PyTorch. We also complemented the feature set with a few different features that we could sort of engineer from existing ones, so digit percentage of the string, special characters. And we also looked at Shannon entropy of the string, so randomness of characters, and we actually found this measure to be actually quite a poor feature. And we sort of found later down the track that some NLP techniques around looking at randomness of strings will probably be superior. So we're looking to use that in the future. So cool. We had a pretty luscious feature set, I guess, and something to start with. So now it was time to kick off our modelling and evaluation. So I'll hand it over to Triss. There you go, Triss.
Hello. Okay, say after you have trained a machine learning model and obtained an amazing accuracy of 90%, how do you know it is performing well on real-world data that the model has not seen before? Does it actually work? So this is why having a test set that represents unseen data is very important. It's a common practice to have to split the data into training set, test set, and validation set. Training set is used to train your model, and test set is used to test the performance of your model on unseen data so that you know how well your model is working. And validation set is used for parameter and model selection. It's common to have around 20% of test set, but that ultimately depends on the amount of data you have. Say if you have a massive data of 1 million rows, 1 or 2% would be equally sufficient. So we have attempted a few models for this use case, and the top performing models are deep neural network, random forest, and word embedding. So neural network with 3 layers and above are considered deep neural network. The layers and hidden units allow the model to learn complex feature and high-dimensional data. Typically, deep neural network requires a lot of tuning, which means you need an extensive knowledge of the model in order to use it. They're usually trained using conventional PyTorch or TensorFlow frameworks. Alternatively, you can use pre-trained models for transfer learning. And libraries like FastAI can make things a lot easier and faster, especially for beginners who are keen to get their hands dirty in deep neural network. On pros and cons of deep learning, so deep learning is known to be very powerful, and it's able to do automatic feature extractions, so you don't need to do a lot of the manual feature engineering. The disadvantages are it requires massive amount of data. It requires huge computing power. The architecture can be complex and hard to tune, and the resulting model may not be easily interpretable, as in you don't know why it does what it does. Okay, and then we have random forest. So random forest is an ensemble of decision trees, which basically means a collection of trees. So decision trees predict the final label by splitting randomly at multiple decision points based on selected features by the model. In this case, having many trees provides a better generalization and reduce overfitting. The algorithm makes predictions by using majority vote of each individual trees. So some of the pros are it's quite commonly used and it gives you pretty good result. It doesn't require a lot of scaling of data. It can handle a mixture of feature types. The cons are the model can be difficult to interpret as well, just like deep neural network, and it's not suitable for high dimensional data. Word embedding is typically used to associate words with their label. For instance, take the use case of IMDb movie review. We are able to find words that are associated with positive and negative review. In our use case, we use character-based word embedding, which creates a vector representation of each character in the URL using multiple dimensions. This was trained using TensorFlow. Okay, so this is the table that shows the performance of the models we have obtained. And as you can see, deep neural network is the winner here. Okay, evaluation method. Here we have a few methods of evaluating machine learning models. So accuracy is pretty straightforward. It's just the percentage of correct prediction over the total number. And then we have F1 score. F1 score is quite the standard evaluation method, especially when it comes to competitions like Kaggle. We think F1 score is most suitable for use case because it takes into consideration false positives and false negatives, right? We don't want our model to give too many false positives to the security analyst because that will slow down incident response and because they will be wasting a lot of time investigating false alerts. F1 score is also preferred over precision and recall because optimizing precision or recall is actually trading off the other. For example, raising the value of precision actually gives you a lower recall value, whereas optimizing F1 gives you a good balance of both. The diagram at the right is an example of a confusion matrix, which shows true positives, true negatives, and vice versa. And here's the confusion matrix for our winning model, the deep neural network. So confusion matrix gives a good visual representation of your model performance. As you can see here, our deep neural network has a higher false negative rate compared to false positive. Okay. And so explainability of machine learning models has become quite an interest lately. Complex models like deep neural network are considered black boxes because it's difficult to know what's going on within the model. Ideally, we want to avoid using models that rely on undesirable features such as those that will lead to biases in production. For instance, in the context of image classification, the model might be relying on a snow background to classify whether a picture has a wolf in it, instead of using the wolf itself. So introducing a library called SHOP. SHOP is a very cool library which allows further insights into the internal working of models. So using this, you're able to get a global or local explanation of your model prediction. Global tells you which features influence the model as a whole, and then local informs you which feature influence the outcome of individual predictions. Here's an example of how it works. So if we could take the meerkat example, the red is positive sharp values that increases the probability of it being a meerkat according to your model, and blue is negative sharp values that reduces probability of the class. So from this, this shows that the model is relying on the eyes to detect whether a picture has a meerkat. You can find out more about this library on their GitHub page, which also contains more examples. Okay, so parameter tuning. What is parameter tuning? Parameter tuning is just trying out different values for your model parameters in order to obtain a better result. take neural network as an example. To tune it, we'll be trying out different number of layers, number of hidden units, learning rate, and activation functions. So we have two main methods of optimizing parameters. They are grid search and random search. Grid search searches exhaustively through a range of values that you have provided and gives you the optimal combination. The downside of this is it takes time and it's computationally expensive. So, and then on the other hand, we have random search. Random search searches through the values that you have provided randomly. And this requires less processing time, but you're not guaranteed to get optimal combination of the values. So now I hand this back to Alistair for the closing bit.
And so our last bit, the deployment, is actually currently under construction, and we're looking at things like Starlet and Flask to build that out. And obviously, as you can see, we're trying to work, I guess, hard on improving our model as well in terms of features and the evaluation we do. Just a few shout-outs to Katie Ford for the wonderful artwork in our presentation, Ig Fang and Paul Morand, who continue to push us, and obviously the wonderful Python community. And yeah, thank you for having us, and I hope you have a great evening.
Thank you for that great talk. So people can come up and ask questions.
Done. Thank you.